So we were saying, okay, so the Fourier transform decomposes any signal as a sum of sines of sinusoids in general. And then this sum of sinusoids, we have to control three aspects of those sinusoids. The first one is the amplitude. The other one is the phase. So the phase controls where they start. And then the last one is the period. The period is 1 over frequency, and it is the distance between two equivalent points. So these 2 points are equivalent because they have the same phase, and the same happens here. And in general, this is the equation of a 1D sinusoid. And then you have the definition. Cuéntanos un chiste, anda. Que llega tarde ya sabe. Te voy a preparar. Cuéntanos.
Es un negro en la nieve.
¿Qué es un?
Un negro en la nieve. Un blanco fácil.
Okay, so 1 over lambda, that is 1 over the period, is the frequency, and the frequency is measured in hertz. And 2 pi over lambda is another frequency, but it is called the angular frequency. It is measured in radians per second. And this will have an impact later. We don't have for images, we don't have these kind of frequencies where we have hertz. We have, for instance, you have units of, but we'll do it later. We'll do it later. Okay, good. Yesterday it appeared this idea that we need to define an inner product. So we need an inner product because the Fourier transform is a change of basis. And the change of basis for orthogonal basis, they need an inner product to define what are the coefficients. So let us see when two signals are orthogonal to each other. We know the concept of being orthogonal for vectors, for 3D vectors, 2D vectors. But what does it mean that two signals are orthogonal? Okay, so let's say that you have a couple of functions. So you have f, and then you have another function g, and the constraint of g is that it is a component of f. So to make a f, you need this sign. So you multiply these two signals point by point. So the product is this red signal there. And then we have to integrate. So you see, the inner product is f times g, but g was real valued signal. So we don't need to take the complex conjugate. The complex conjugate of a real number is the same number. And then we have to integrate. And this goes from minus lambda half, lambda is the period, so minus period half to the period half. Actually, it doesn't matter where you integrate. You can go from 0 to lambda, from minus lambda half to lambda half. As long as you have a full period, you will get always the same interval. Okay, so now you multiply point-wise. This is this red line, and now you compute the integral. And this integral is different from 0. So different from 0. So if I want to compute f of t will be some number, I don't know, 0.7. That integral, let's say, is 0.7 times g plus some many other things. Okay, then let's see another example. Now, let's consider instead of g, we consider this other function h. Okay, And then we do the same. We compute the inner pointwise product between the two functions. So at every time t, we compute the product between f and h. And this is this red function there. And now you compute the integral. But this integral is 0. So that means that in this decomposition, we have 0 times h. So h is not a part of f. Okay, so in this decomposition that we did before, in this decomposition of this square signal, all these signs are components of the square, while there are some other signs that are not components of this square. Okay. Okay, good. Then, yeah, you can compute. So, let's say that we will construct, or we will use a basis that is made of sines and cosines. So, f will be your square, g will be a particular sign that you are looking at, and then you are computing this inner product between the two, and the same for cosine. So g now is a cosine, and now we construct the basis that is this one. Okay, so instead of using sine or cosine, that are functions we are used to, we take this exponential. Okay, so let us see. So we take now g will be, let me see how I wrote it, 2 pi. Okay, I will write it like this, and then say omega is 2 pi. So it is much simpler to write that. Okay, so now we have to compute the inner product between these two functions. Sorry. And this is the integral from minus lambda hat to lambda hat of f of t, and then g star. Star is complex conjugate. Okay, now this is the integral from minus lambda hat to lambda hat of f of t and x minus j omega t. Do you agree with that? And you may immediately recognize this is the Fourier transform. This is the Fourier transform of f. So let me write it like this. This is the Fourier transform of f evaluated at omega. Okay, so the hat means Fourier transform. You can also write it like this. So this is Fourier transform, or, and when it is an operator, we use the curly brackets of f of t.
Fourier transform, the limit of integrals should be infinite.
The Fourier transform of
Signal.
but should be infinite when?
But the signal is
anything.
I mean, it depends on the length of signal. And I don't see how we can match this with Fourier transform if we have as the limit of integrals lambda divided by 2 and minus lambda divided by 2.
You mean that this limit should be, yeah, actually you're right. This is the series, Fourier series, not the Fourier transform. For signals that are periodic, this is the Fourier series, not the Fourier transform. Yeah. Now, I thought that you were referring that this integral has to be smaller than infinity. And there are a few signals for which it is not smaller than infinity, it goes to infinity. Okay, then what else? Okay, so this inner product here is the Fourier transform. It is the Fourier transform when G takes this form. Okay, and then this is the same idea that Fourier transform or the Fourier series. I normally use them interchangeably, but to be strict, they are Fourier series. So the Fourier series of a periodic signal is nothing more than the inner product between the function you are analyzing and your probe, your basis function. Okay, good. Okay, then this integral will be in general complex. Okay, so this integral, because it has a complex integral, it will be a complex number. It will be a number. Okay, so let's see. Let's see how we can decompose our signals. Okay, so we can make this decomposition. So we can take f of t, you take the average, so this A0 is the average within a figure. And then you have this infinite sum. And this infinite sum is using two bases. So one is the cosine, the other one is the sine. And then you have these two coefficients that are real numbers. And these two coefficients, we already know how to compute them. So it is simply the inner product between the two. Okay. Then let us use the complex basis, not the real ones. So they are very much linked. So we can use the complex basis or the real ones, these two, and both expansions will be equivalent. Okay, so let us do it step by step. It is more easy. Okay, so let's say that this integral here is some particular value that we will call in red. We will call it CA to be consistent with the slides. Okay, so now we have that the Fourier signal f of t will be. Let's concentrate. It will have some A naught, that is the average, but let's concentrate on the rest. So the rest is from 1 to infinity. Clear? I need this one letter. So Cn and Eg omega. And let us see why this is the same as what we had yesterday. So what we had yesterday, let's do it here. So we have a vector R was the inner product of R with U1 divided by the norm of U1. 1 plus the inner product of R with U2 divided by the norm of U2 plus all the rest. Okay. Here we have the same. So this part here is this one. Then this part here, for that particular base, is 1 or 2 pi. Depends on how you scale. So it depends on whether you put here 2 pi in front or not, but it is 1 to simplify. And then we have the basis. So this part here is this one. You see? So we have the Fourier coefficient normalized and then times the basis. And that is what we have there. Okay, so now I have skipped the 0, the average, because it is included here. If you put n equals 0, then this is 1, and then C0 is the average. Okay, then let us expand this a bit. Okay, so we have let's say that Cn is a complex number. In general, it will be something like this. So it will have phase and an amplitude, and then we have this. Okay, then we will have C0. Now we have it as we have wanted before. Now there is a constraint you may remember from signals and systems. That is, if f of t is real, so if f of t is real, then Cn is equal to C minus n star. Remember this. This is called the Hermitian symmetry. Okay, so that means that I can add this from, instead of going from minus infinity to infinity, I will go from 1 to infinity. And I will do the following. I will put both terms at the same time. So I will put Cn, so then the one Cn is this one. And I will put the one of minus n. So let us write it first. The one of minus n. Okay? So we have, instead of going from minus infinity to infinity, I go from 1 to infinity, and I keep both here. And I keep the n and the minus n. Okay, now, because the signal is real, these two numbers are the same. So this one and this one are the same. They're equal to each other. Because the module of t is the same. And the phase is one is the negative of the other. Okay, so that means that I can rewrite that as, let's do it. So it will be C0 plus some 1 to infinity of what? Cn. And then well, this term is the same. And I will write it already like this. And what else? Now, Cn again, because the amplitude is the same. But now the phase is the opposite. There is a minus somewhere. There's a minus here, and then there should be a minus. And then the other one the opposite. Okay, so again, I will put these two together. So I will put all these together. This is minus J 11. And then what can we do with this? Okay, so let's separate these into these two terms. So C0 plus sum. Okay. And now we have Cn in front. Now we have E minus J omega n. Actually, it is annoying that I don't have the same sign. There is a small manipulation I'm missing. But at the end, you can separate these two. You can separate into cosine and sine with the same sign. So I must miss some sign somewhere. But you can separate them into cosine and sine. What I wanted to show is that even if you are dealing with complex signals, all this Fourier transform is a complex thing. You end up representing real samples, real signals. And the trick to do that is this emission symmetry. So this emission symmetry is the one that allows you, by using complex numbers, to represent real signals. Okay, then, with time, I'm sure I am able to do it and you to make this derivation. It is very small derivation. Okay, then what is the meaning of these complex numbers? So the amplitude of the complex number is the amplitude of the sinusoid, and this was already seen here. The amplitude of the sinusoid is missing also the Cn. So the amplitude of the sinusoid is the module of Cn, and this appeared in our derivation. You see, the Cn is in front. Here, the Cn is in front all the time. So that is the amplitude of the cosine. What about the phase? The phase. So the phase of this complex number goes into the sine and into the cosine. So it is shifting the sine to the left or to the right. And this is the same. Yeah, this is the extension of the Fourier transform. So the Fourier transform, now the limits are minus infinity to infinity. The other one was the Fourier series. But actually, they are very much related, so that is why I also interchanged them. But it has the same kind of concepts. And it is interesting that if you take different organs are sensible to different decomposition or different parts of the signal. So, for instance, sound. Our ears, you can take any sound. So this sound, you know that this representation that we make normally of sound, it is what is the local pressure of the air at a particular location in time and space. So this representation you can decompose into sum of sines and cosines, and it turns out that our ear is only sensitive to the amplitude, not to the phase. So you can take a sound signal, you make the Fourier transform, you randomize the phasing, and still you hear more or less the same sound. more or less. It is not exactly the same sound, but we are very little sensitive to the phase of sound. But with images, it is the opposite. With images, we are sensitive to the phase, not to the amplitude, or not so much to the amplitude. Okay, then with discrete signals. Discrete signals are almost the same. So let us put it here. Okay, so let's say that we have a discrete signal like this. So we have something that is periodic. Okay, so it goes 0, 1, 3. 3 will be n minus 1. And then at n, you have a repetition of the same thing. And then you have the repetition again. And here on the other side, it is the same. Sorry. Yeah. And then this is minus n. No? Minus n, minus 1. Okay. And this is x of n. And this is n. Okay, now we have to define the inner product, but now with discrete signals. So with discrete signals, we will have our discrete one, and then our basis. And the basis that we will construct will be this one. I think it is more easily recognized in this way. So all this frequency here, is called omega k. And you see that it has this k times 2 pi n. So this thing is kind of the fundamental frequency. And it will have another implication in the Fourier transform. We will see it now. Okay, now, again, this signal is periodic, so what we are constructing here are the Fourier series, not the Fourier transform. But now we have to define the inner product between two discrete signals. Okay, so in general, if we have two signals that have periodicity n, then this inner product between x and j, let's say, is the sum over a period, and now a period is discrete, of x of n so this is now our inner product. Another Fourier transform. The Fourier transform is simply the inner product between your input signal and this basis function. And everything that we did before with this expansion, it applies. But now, only that we don't have to go to infinity, we only have to go to n. Because there are only n functions like this. Let us call this one. Let's call this one. Let's call it omega n, or wn. So wn has different values for 0, 1, and minus 1. If you compute what is wn, capital N, this is the same as w0. Now it is very easy to see. So let's say, what is w0? Okay, so that w0 is a j 2 pi times 0 n. Okay, but this is 0. So this is 1 all the time. So this is this function. This is this function. That is 1 all the time up to n minus 1. You see, because the argument is 0, so exponential of 0 is 1. And then it is 1 all the time up to from 0 to n minus 1. What is wn? Capital N. Okay, so audio capital N is N 5 capital N percent. But this is these two cancels, and this is AJ 5 to the power N. But A the E to the 2J to pi power, this is 1. This is 1 to the N, this is 1 to the pi again. You see, so there are only N minus 1 or N different bases of this one. Because at some moment they start to repeat. I'm sure you did all these reasonings in discrete signals, right? Have you done it? Okay, this is just a reminder of everything that you already know. Okay, but now the Fourier transform or the Fourier series is this one. What does it mean? Okay, so what does it mean that we have let me introduce the Fourier transform first, and then we'll relate the two. Okay, then Fourier transform. So the Fourier transform, this is, we said this was Fourier series. Fourier series. Now let's do the Fourier transform. Okay, so the Fourier transform would be x of n. But now we don't have a discrete set of angles, but we have a continuum set of angles. So we have any possible angle. Because of that kind of reasoning, that omega cannot take, omega k cannot take, or the n, the k cannot take any value. For the same kind of reasoning, omega can only take values in the range 0 to 2 pi. Because outside that range, it is periodic. Okay, this is the Fourier transform. And that is defined, and we have to define the inner product. So now the inner product goes from minus infinity to infinity. X of n, and then this time, where g is this exponential. But now we go from minus infinity to infinity. Okay, so what does it mean in terms of plots? Okay, so let's say that you have a signal like this. So you have this typical signal. I'm spending a lot of time in one dimension because we already know, okay, and just a reminder. And then we will jump into 2 dimensions. And then the Fourier transform of that, is normally called xj omega. The module, because I cannot plot complex numbers. Let's put names. This is n, this is the axis omega. Would be something, we plot it like this. We don't care, this is a specific case what that Fourier transform is. This is kind of generic Fourier transform. And we normally plot it between minus pi and pi, but we said that it is periodic, so at 2 pi, we have the same. And at minus 2 pi, we have the same again. Okay, so what does it mean that instead of having a continuum, here we have, let me use a different color. I will use green. We have a discrete set of values. That means that in the continuum Fourier transform, we are taking samples. We are taking samples that are separated 2 pi over n. So this is kind of delta omega. And then what we have here is 0, and then 1. I'm backing out of space. Great. So here we have 1 delta omega. Here we have twice delta omega. All the way up to here, up to n minus 1 delta omega. That is just one sample before 2 pi. So the fact that we have before Wn equal W naught is the fact that this 2 pi is equivalent, totally equivalent to this point. Okay, so yeah, actually it doesn't matter if you give as the Fourier transform, you give this period, or if you give this other period here. So as long as you give a full period of the Fourier transform, you don't care which one it is. You have to say which one it is, but you have the same information in both. Okay, so I think we have all. Then let's go back to the slides. So here we have the same things. So this is the Fourier coefficient, that is simply the inner product of the two. And yeah, this is the Fourier coefficient. And here you recognize something. It is 8k times this thing. And then divided by n. Why divided by n? It is the normalization factor. So the norm of this vector is n. So you have to divide by n. Now this is the Fourier coefficient, and then once you have the Fourier coefficient, you simply have to multiply the Fourier coefficient by the basis function. That's it. So this is the Fourier series, because it goes from 0 to n minus 1. And so this is all the same reasoning that we have been doing. Okay, now we have made use of the fact that these basis functions are orthogonal to each other. So that means that if I take two exponentials of this form, omega 1 and omega 2, and I compute the inner product between the two, the inner product is 0 if the two frequencies are different, so that means orthogonal, and it is different from 0 if the two bases are the same. And the same here. So the same if you do it with discrete signals. So if you take two basis functions, this is on Wj, this is Wk, and J and K are different, the product between the two is 0. So this sum is 0. And if they are the same, then it is a constant that we know it is already n. Okay, then. Okay, now let's say that we have images. We don't have continuous signals, or continuous 1D signals. We have a continuous signal. Okay, so how do we extend these two images? Okay, so let's extend all these ideas to images. Okay, so now we have an image. Let's call it I. And now we refer to it with I of R. Okay, and R is X and Y. It's a vector that tells you where you are in space. Okay, so this point will be the point R. Okay, now I need to define a basis that is kind of sinusoid. And we will see that a suitable basis for that is this one. Okay, before we had here, we have one time axis. So this is real space. We have one time axis, and we have one frequency axis. So we have the frequency omega. Now we have two time axes. We have two time axes. We have the axis y, and we have the axis x. So now we will need two frequency axes. We will have one that we will call omega x and one that is omega y. And if you have three time axes, you will need three frequency axes and so on. And in general, so now this R will be the frequency. Okay, I like the letter R, but for the explanation today, let us use something different that is more similar to what we know. I will use a vector of frequencies. And this vector of frequencies will have omega x, omega y. And this inner product is well defined. It's just a standard inner product between two the vectors. So this is aj, and then omega x plus omega y y. And in general, it has this expression. So for any dimensions, it has this expression. Okay, so now this will be my basis function. I have an image. So let us construct the inner product between the two. So I want to construct the inner product between my image. And for the moment, let's use another image, R. And now we copy from what we know from the other Fourier transform, from the one-dimensional Fourier transform. So you have to go from minus infinity to infinity, but now I have two axes, so I have to do a double integral. And let's see if this works. This is a suitable inner product between a 2D signal and another 2D signal. It is the same. It is the same definition that we had before, only that I have to take care now that I have two dimensions, and then I have to do a double integral, and my differential element has to go in two dimensions. But it is the same. Now we have defined Fourier transform for images. Yeah.
We use Fourier transform for signals in order to work in a frequency basis. Because sometimes what we need time domain is that frequency. But for images, why would we choose to?
You will see over time. So give me some more lectures and you will see why. But it will be the same. So there are features that in real space they are not so visible. And when you do the Fourier transform, they immediately are visible in the Fourier domain. Okay, then now we have the Fourier transform. So all we have to do, if I want to compute the Fourier transform of an image I, all I have to do is compute the inner product between I and these basis functions that I have here. And if you want to do the inverse Fourier transform, if you want to recover, so let's call these, I transform, and now the new variable is omega. Okay. So this function this function here depends on r and omega, because omega is inside, okay, inside the d. So it depends on r and omega, but I'm integrating in r. So the only dependence is on omega. So the Fourier transform depends on omega, and it is a complex number. And we will see what it means, what this complex number is. But it is a complex number. So if I want to recover the image, what I have to do is the inverse Fourier transform. So the Fourier transform -1 apply to this one. Let's make it great. Apply to this one. It will be the opposite. Okay, so now, how do I reconstruct the vector? Let's go back to here. Where is it? Here. Okay, I want to reconstruct this vector. This is our image. These are the Fourier components. So what do I have to do? I have to go over all the frequencies, over all my bases, and then I have to add all my basis functions times my Fourier components. Okay, so adding in the continuous world is an integral. So I have to go over each one of my basis functions. My basis functions are defined by omega. So I have to go over all omegas. And for each one of them, I have to take the Fourier transform. So this is the coefficient integral. And I have to multiply by the basis function. And the basis function is this one. You see, it has the same structure that we did with vectors. Exactly the same structure. So you put your coefficients in front, you put your basis function, and then you add overall basis functions. So now we have the Fourier transform in n dimensions, 2 in the example, but these expressions are general. You can construct 3D signals, 4D signals, whatever. So a 2D signal is an image. What is a 3D signal? Can you think of an example of a 3D signal?
A video.
A video. In a video you have 2 dimensions, that is the image, and then time. What else? A volume. If I make an X-ray computerized tomography of any one of you, for every point in the space, I know what is the density. And then I have 3 dimensions. 4 dimensions. A volume with time. So I have a volume, and then I see how it evolves over time. And then I have 4 dimensions. And you can compute the Fourier transform in 4 dimensions, in 3 dimensions, in whatever number of dimensions you like. Okay, so let's make a break here. 10 minutes, so we come back. Let's continue. Okay, so now we have our 1D or 2D exponentials and Fourier transforms. So now let's extend some of the ideas that we had before. So one of the ideas was that these basis functions, they were orthogonal to each other. So that means that if I compute the inner product between one of them, this is one, and another one with different values, this inner product is 0. And that is why the Fourier transform has relatively simple expression. Okay, so what if my image is discrete? So I have a matrix. I don't have a continuous signal in space. I have a matrix, and we have already seen this red, green, blue channels, and so on. Okay, so now our image will be made of pixels, and they go from 0 to C minus 1, from 0 to R minus 1. So this is number of rows, number of columns. And let's see how the exponential was made before. So the exponential was, so for 1D signals, it was like this. And this was a k, two values 0, 1, and minus 1. That was 1D. Okay, so now that we have 2 dimensions, how do I expand that idea? Okay, so let's say that this is the axis, this is the axis y, this is the axis x. Okay, so now, what was n before? N was the length of my signal. But now I have two lengths, one in y, one in x. So I will start with y. So now it is the length in y times k, at ky. K was a parameter that I could choose. And then n. But what was n? N was time. But now n has to be the location. So it will be times y. And now I will have another component that is equivalent for x. So now the length in x is c, and we have some other frequency, and then times x. So this will be my two-dimensional sinusoid, and kx, ky goes from 0, 1 to r minus 1, and kx goes from 0, 1, c minus 1. So it is equivalent. And if I want this vector notation, I can say that this is a, j, and the inner product between omega, now I have two axes, omega k times r, and r is x and y, so this is x and y, this is omega kx, omega ky, and when you multiply these two, what you get exactly is this one. You see, omega kx will be this part here, so 2 pi kx divided by c, and this one will be 2 pi ky divided by pi. So we have again our favorite notation using vectors. And the same orthogonality applies. So if you compute the inner product between any two discrete sinusoids that have different frequencies, the product will be 0. Okay. This is what is said here. So here they are presenting the two sinusoids. I'm using R and C because I think they are more clear. And later he's using also R and C. Then the orthogonality between continuous and the orthogonality between discrete. Yeah, this is more the repetition of what we had before. So if I want to compute the Fourier transform, he's using U and V. I prefer omega x, omega y. So if you want to compute the Fourier transform, you compute the inner product between f and your basis function. If you want to reconstruct your image, then you have to go over all basis functions, multiply that basis function times the Fourier coefficient. And the same for this group. So if you want to compute the Fourier transform for a discrete image, then you have to compute the inner product between your image and your basis function. And this basis function we have already introduced. And if I want to reconstruct, I have to take the Fourier coefficients and multiply them by their corresponding basis function and add over all basis functions. So all this is the same, and it is the same as what you already knew for 1D signals. Okay, so let's see some examples. So, or some extra ideas, and we will see examples later. Okay, so this is the continuous pair of Fourier transform. So this is the forward Fourier transform, this is the inverse Fourier transform. So here we integrate the image, and you have to be careful with this. So if you are integrating the image, your differential will be in real space, and then you will get the Fourier transform, whose argument is frequency. And then if I want to go back, I take the Fourier transform that is now in frequency. I have to integrate over frequency, and I will recover my in real space. Okay, so what is the assumption here? So you may see that these integrals, they go from minus infinity to infinity, but my image doesn't go from minus infinity to infinity. So what it is assuming is that, for instance, let's say that the origin is here. So the origin, the 0, 0 point is here. So this R starts counting at 0, 0. And then my image occupies a region in a plane that goes to infinity. But outside my image, the rest is 0. So I don't have to integrate anymore because I'm adding zeros all the time. Okay, what about the discrete images? So discrete images, this is a way of understanding them, but I prefer this one. Okay, so let's think again of 1D signals. That is something we know well. Okay, so we had a 1D signal that was repetitive. Okay, so it was periodic, and it was all the time the same. Okay, this we already know. This is x of n. And this is n. So I can think of this as I have some kind of unit signal, but it's repeated all the time. I have the same signal repeated all the time. Okay, now let's think of images. So, and I have an origin point. Okay, so I have an origin. I have n larger than 0, n smaller than 0, and so on. Okay, so now in images, I will need the same. So I will need a coordinate system, now with 2 axes. So I will have y, and I will make more space for this. So I will have y, I will have x. This is x larger than 0. This is y larger than 0. And the other sides are y negative, x negative. And then I have my image here. So my image is something that goes, this is my image, and it goes from 0, let's do it here, goes from 0 to r minus 1, and it goes from 0 to c minus 1. So this is the equivalent of this unit signal. So let's make it red. That we use the same colors that we had before in 1D. So now it has to be repeated. So now I have this image repeated all over the place. And it is the same image that is repeated all the time, but now in 2 dimensions. I will continue to infinity. Okay? It is the equivalent of this. Okay? So I have a unit signal that is repeated all the time in both directions. But now I don't have 2 directions, left and right, but I have also up and down. So I have to repeat it in all directions, up, down, left, and right. So, and they would go to infinity. I will not draw it, but they would go to infinity. And this is a way of thinking of the following. Okay, so what happens here? What happens here if I keep traveling in this direction? Okay, so I start at this point. I give 1 step to the right, 1 step to the right. When I give 1 more step to the right, I see the same point that I was watching at the beginning, and then the same happens here, and the same happens here. Okay, so every time that you go out of the unit signal, you start seeing the same signal again. This is what is happening here. So if I start at this point and go to the right, at some point I start again. When I keep going, at some point I start again. Okay, let's do it in the other direction now. So the same happens. So if I think of this, I see it again as the following. So instead of keeping going to the right, if I go out of my unit signal from the right, I come back to the beginning. So if I go out from the right, I go in from the left. Do the same. And if you go 2 steps out on the right, it is the same as if you come in 2 steps from the left. And the same happens if you go in the opposite direction. So now you start at this point, you go to the left, you go to the left, and then you go to the left, but you have come out by 1 step on the left. So it is the same, this sample is the same as if you come 1 step from the right. So these 2 samples are the same. So now if you travel in the other direction, so you start here and you keep traveling, at some point you go out from the left, but this point on the left is the same as this point on the right. Okay, so why this is needed? Okay, so you may think of this periodic signal in the way I showed you, so just by repeating the signal, or by putting your signal in, let me do it first in 1 dimension. Let's say that I want to represent this periodicity in a different way. I could do that by taking my periodic signal, the basis of the unit 1, this would be x, and then you turn it around on a circle. I put it on a circle. I'm very bad at drawing. So you put it on a circle. You start here. So I will put, this is n equals 0, this is n equals 1, n equals 2. So here I put n equals 0. Then at 120 degrees I put n equals 1. And at 120 degrees times 2 equals n equals 2. And then if you start traveling, you go from here to there to there, and then you come back to the same point. You see? Actually, this reminds you of anything. This is the set plane. Have you done x of n, I put the set transform of x of n, and I get something that is x of z. This is the set plane. That is what you are doing in the set plane. Okay, so I can make this image repetitive, periodic, by putting it in a circle. But now in 2 dimensions, I need 2 circles. So I need one circle in 1 dimension and another circle in the other dimension. So I can think of this image and the periodicity of that image as being laid in a torus. But this is more kind of a strange way. But it has the same properties. So let's say that you start at some point, you keep traveling, but when you are done with your image, you start at the same point where you started. And the same happens if you go in this direction. So at the end, you reach the same point. So, but I think this is a more weird way of thinking. So I prefer this one. I prefer this one in which an image is simply repeated all the time. Okay, good. Then, yeah, this is the same. The complex sinusoids we introduced before. Okay, so now let's look at these sinusoids. Okay, so the Fourier transform makes the same promise as it does in 1 dimension. So in 1 dimension, it says you will have a signal can be decomposed as a sum of sinusoids. Okay, so here it is the same. A signal is, an image is decomposed as a sum of sinusoids. And let's see those sinusoids. Okay, so what is a sinusoid in 2 dimensions? Because I know in 1 dimension, but not in 2 dimensions. Okay, so let's start with the basic sinusoid. This is the expression we had before. V and U, they are the frequency components in Y and X. And for simplicity, let's make them to be the same. So R and C, let's, for the moment, only consider square images. And then the V and U, this is higher. The V and U that are 2 frequencies, so those are in the frequency plane. That is a point. So now, instead of the XY plane that we are using, so for our images, we are now used to represent them in this plane, we will represent them, I'm using red for Fourier transform. So we will represent them in omega X, omega Y, but they are calling V and U. Okay, so you take a point here. Now this is a frequency. So if it is a frequency and it is a 2D point, I can represent it as a vector, as in polar coordinates. So in polar coordinates, it will have some module omega and some radius theta. So omega x is omega times cosine of theta, and omega y is omega times sine of theta. Okay, so let's do that. Now I have to decompose u and v as omega cosine theta, omega sine theta. Yeah, this is just how do you compute omega theta? Omega is the module of the two. If you have a Cartesian coordinate, omega x, omega y, how do I compute omega? So omega is the square root of omega x squared omega y squared. And then theta is the arc whose tangent is omega y divided by omega x. That is what is said there. Theta is the arc whose tangent is v divided by u. It is the same. Okay, so now I have omega. This is this radius there. Then let us compute something that is similar to a wavelength. So I will compute lambda, that is n, because we are in a square image, divided by omega. And then all these sinusoid can be written in this way. So actually, a complex sinusoid has a real part that is sinusoidal and an imaginary part that is sinusoidal. Okay, so let's plot it. Let's plot the real part, for instance. So let's separate the real and imaginary parts. And this is what we have. So I'm plotting only the real part of it. Okay, so let's consider this expression. So it is for every R and C in the image, you have a value. Okay, so you simply substitute R and C, and let's say that theta, lambda, and phi are fixed, and the amplitude are fixed. So you fix the amplitude, you fix the frequency, that is lambda and theta, and you fix the phase. And now you are very patient, the computer can do it very quickly, and evaluate this function at every single point R and C, and you plot it. That is what you get. And here you recognize already the components that you have. So, for instance, it is a sinusoid in the sense that the intensity goes up and down in a sinusoidal way. So, if you go in this direction, what you have is a pure sine. So, it goes up, and then it goes down, and then it goes up, and then it goes down. But it is a sinusoid, as it should. So, it is a wave. What else? It has an amplitude, so how far it goes up and down depends on this number here. So if you make that number to be very small, then the oscillations will be small. If you make it large, then the oscillations will be very large. Okay, so you will have a lot of contrast or very little contrast. And the period and phase, I think they are better explained in some other slide. Yeah. Okay, so now the frequency was determined by two parameters. Lambda, that was omega. Okay, that was a relationship between omega and lambda. There is a relationship between lambda and omega. So if I tell you omega, immediately I'm telling you lambda. It has two components, omega and theta. So what is theta? So theta is controlling the direction on which this wave is propagating. So if you make theta to be pi divided by 8, that is pi is 180 degrees, so this is 22 degrees. So if you make theta to be 22 degrees, then it is a wave that propagates along 22 degrees. And if you make it larger theta, then you would orient towards that direction. And what is the phase shift? Okay, so what is the phase shift in one dimension? Okay, so let's think of sine. So let's say that our sigma is sine of omega t plus phi. And I make phi equals 0. So x of t for, and this is t, for phi equals 0. So for phi equals 0, it is a sine. So it goes like this. Okay, let's make it phi equal phi half. And then it is a cosine. And then what I'm doing is shifting it phi half in that direction. And then it goes, I'm very bad at it. The important part is here. The one that I can draw very well is this one. So it starts at 1. This one is starting at 1. But this one is starting at 0. Okay, so what we are doing is simply by the phase, I am shifting this to the right by half. Not this one, not to the left, not to the right, but to the left. We are shifting to the left by half. So now the same applies with to the sinusoids. If you change phi, what you are doing is controlling, if this is your origin, where the maximum is with respect to the origins. So here, with phi equals 0, it is at the maximum is at the origin. If you make phi something different, now the phi, the sinusoid is shifting to the right or to the left, but in the direction of the propagation. Okay, so it is shifting along this direction. Now, I have images. So I have an image. I can do the Fourier transform. How does the Fourier transform looks like? So you will have complex numbers, but you cannot plot complex numbers. So I will take the real part and the imaginary part of those two images, and plot the real part on one side and the imaginary part on the other side. And here you have the frequency axis, so the origin is at the middle, and then we had before, so in the image we are not showing that, but let's think of the Fourier transform of a 1D signal again. So we have a 1D signal, whatever it is. So this is x of n, and then it is 0 all the time. This is n, and the Fourier transform, that is always red. The Fourier transform is something like this. So we go to phi minus phi, and then it is repeated. Okay, so when I have a Fourier transform of a, we will talk much more about this, but let's already introduce that. So when I have an image like this one here, and my origin, let's say, is here. So this is y, this is x. The Fourier transform, that is red, it will go from minus pi in omega x minus pi in omega y. The origin is here. This is the origin of omega y, omega x. And then it will have this shape that I will go with the shape. Okay, so this is the equivalent of this part. So it also has an origin that is in the middle of the Fourier space. It also has some extent that is simply whatever we have This of course omega, this is x3 omega. So in the Fourier space for 1D, it goes from minus pi to pi, and for images 2, but now in 2 dimensions. So this is that. They have reoriented the axis, but we don't care. So now omega x goes there, omega pi goes there. And this is the real part and the imaginary part. But instead of this, we can take the amplitude and phase of these Fourier transform. So let me switch to my computer. I will stop sharing here. Here it is, the imaginary part and the real part of that. You see? And this is the power spectrum density. The power spectrum density is the module of this complex number. And now you can make a cut here. You can cut, so this is a 2D signal. So I can draw along a line. So I can take this line, for instance, and compute what is the amplitude along that line. And then it will be a 1D signal. The axis is 1, it is not frequency. We will come to the units of frequency at some point. And then I can plot what is the phase, for instance. So I'm taking any value here. So I'm taking a line. And for every line, I have a line of complex numbers. And what I'm plotting here is the phase of those complex numbers. So you can compute, or you can plot the amplitude, or you can plot the power spectrum density, that is the square of the amplitude. Or you can plot the imaginary part, or the real part. So you can plot whatever you want. Okay? But those are complex numbers. And also something, let me stop sharing. So instead of the sharing, so now, instead of plotting the real and imaginary parts, I can plot, I can plot the amplitude, for instance. So you take the real and imaginary part and you compute the amplitude of those complex numbers, and this is what you get, for instance. So this is your image, this is your Fourier transform. And in this Fourier transform, we already recognize many interesting features. So for instance, what the Fourier transform says is your image is composed of sinusoids. Okay, and now we know how the sinusoids look like. Okay, so let's decompose this house in sinusoids. First thing is the wall. Okay, so the wall of the house has a sinusoid. And it has some sinusoid that is traveling in this direction. So that means traveling in this direction means theta equals 0. So theta equals 0 should be here. And actually, it is in the middle of the space, in the sense that this is the origin, and this is the middle frequency. So it could be a larger frequency. So larger frequency means larger, quicker oscillations, and a smaller frequency means a smoother oscillations. Okay, so this wall is this point. You need a lot of energy. Having a lot of amplitude means a lot of energy. So you need a lot of energy from this frequency here. Okay, good. Then what else? Then we have the door. Okay, the door has theta equal 90. So it should be along this line. And actually it is the maximum frequency that you can have. So you cannot go faster in one dimension think of the following, which is, so we have said that these are our sinusoids. 2 pi n k and n. These are our sinusoids. Which is the fastest sinusoid that you can have? Which is the k, so that this oscillates the quickest. And half. Okay, so if it isn't half, then this will be 2 pi over n and half n. So this simplifies. And this is minus 1 to the n. So it is a sinusoid that goes like this. It goes like 1 minus 1. And then 1 again, and then minus 1 again, and then 1 again. You cannot go faster than this. So all other sinusoids, let's think of any other sinusoid. So let's say this one. So you would have samples, and they smoothly go from 1 to minus 1. So to go from 1 to minus 1, it takes a few samples. But here, to go from 1 to minus 1, it takes 0 samples. In just one step, we are there. Okay, so this door is the fastest you can have. You go from black to white in 1 pixel. So that means that you have to be at n half. N half is here. That is pi. Actually, in our it was in here. Frequency, the frequency of the sinusoid was pi. And the frequency of this pole is pi too. Okay, let's look for the rest of the object. So let's look for the windows. This window should be this one, and this window should be this one. What about the roof? Okay, so the roof goes in this direction. These are on this line, but the roof has a property. It is not symmetric. So all these features here, the length of the white and the length of the black are more or less equal. So just with one sinusoid you can make it. But this roof is not symmetric, but it is periodic. So you will need a fundamental frequency and its harmonics. So you will need fundamental frequency and the harmonics. You see? So the Fourier transform is already telling you a lot about how an image is composed. Natural images are not like this, but they can also be decomposed in sinusoids in the same way, and you can annotate how much energy you need from any one of those frequencies. So you will need a lot of frequency, a lot of energy coming from these slowly varying sinusoids that are close to the origin. And then as you go farther and farther away, you need less and less of energy.
How can we link this image, for example, with sinusoid? Before we saw like some black band and white band and the periodicity of them, but here they are like.
But it is the same as with 1D signals. So in 1D signal, I'm talking to you, and there will be some 1D signal here, and we can do the Fourier transform, and we can say, okay, whatever I'm saying to you is a sum. A sinusoid in its sum is a beat with these different tones. And what I'm talking to you is a sum of beats. You see? So it is like I think here. So an image, whatever image it is, this is sum of sinusoids. So it is surprising. So you make many beats of different tones, and the addition of all those beats is a speed. Okay. This is really surprising. But for images, it is the same. Thanks. Okay. Let's see a bit more. Okay, so now, for simplicity, we made the images square for forgetting about having different R's and C's. But what if they are not a square? So if they are not a square, then lambda, so omega is 1 over lambda, where lambda is the length of this vector. Okay, so C divided by the frequency in X, R divided by the frequency in Y. And the orientation of the waveform, this arctangent, is the arctangent of this ratio. We are here. And here it is the same idea, but now with a bit of mathematics. So, but what is interesting here is that now we have different frequencies and different wavelengths, and we will see. Okay, so you have a frequency, these are columns, so you have a frequency associated to X. Then you can compute a wavelength associated to X, and a wavelength that is different associated to Y. And then you can have the wavelength associated to the waveform. And I think this is more clear in this example. Let me look for an exaggerated example. Yeah, here we have it. So we have 3 wavelengths here. So one in X, so let's say that you have this wave. So you have in X, you have a wavelength that is relatively short, you see? With this length, I have the same point. But now if I look at in Y, to look for an equivalent point, I need much longer distance. So I need all this distance to find an equivalent point to this one, but not in X. In X, I find it much more often. So I have 2 wavelengths, one in X, one in Y. And I have another one that is in the direction of propagation. So in the direction of propagation, the wavelength is none of these 2. And this is the relationship between the 3. So you have one in X, one in Y, and one in the direction of the wavelength. And the same for frequencies. So for frequencies, you have one frequency in X, one frequency in Y, and one frequency in the direction of propagation. And then, what is the theta, which is the direction of propagation? Is this one that combines the frequencies and the size of the elements. Any questions? I think it is enough for today. Tomorrow we will continue with this Fourier transform.